Tonight's talk is going to be about sort of start the beginning of the year just on telescopes, which is fairly fundamental to our hobby, I guess. So this little handwritten text here, believe it or not, is the patent application for the first telescope, or what was believed to be the first telescope. But the patent application in the Netherlands was rejected because the telescope that was invented was really a spyglass, but they had the idea of an objective lens and an eyepiece. But a number of other spectacle makers objected to Hans Lippershey's application because they said they'd already done it, and they claimed to have brought witnesses. So in the end, we don't actually know who really did invent the telescope. Hans Lippershey is the most commonly cited person because he did actually go to the trouble of making a patent application. But of course, an invention like this, people realised that it had a lot of civil military use. It was the type of scope they had originally was really a spyglass. They'd only get a magnification of maybe 3 times. But the knowledge of this spread really rapidly, as you can imagine. And an important person who heard about it was Galileo in Italy. And Galileo did a lot of work improving the original design, and he was able to go from about 3 times magnification in the original telescope to 10 times, which is roughly equivalent to fairly common binoculars these days. So it's kind of interesting, a bit of history. And this is an image of 2 of the telescopes Galileo made. I believe they can be viewed in a museum in Florence if you ever get over there. And you can see they're very small objective size. And the reason for that is that these telescopes use a single piece of glass for the objective lens and also for the eyepiece. So the reason why they couldn't go to larger objectives in those days, we'll get on to a bit further. So this is the basic design. It's not to scale or anything. Obviously the length of the telescope to the objective diameter is way shortened here, but this is the idea. You can kind of see how it works if you follow the idea of ray tracing, that the object at a distance hits the objective lens and then gets focused. And then you notice the eyepiece lens was a negative lens. There is an advantage of using a negative lens as an eyepiece. We don't do it these days. Is that you get the image the right way up. So it is useful for terrestrial use, but it doesn't really make any real sense when you're looking at the sky, because it doesn't matter which way things are presented on the sky. And the downside of doing it is that it creates a very narrow field of view. But if you follow what the eye observes, you can see the eye without any optical aid sees the image of what you're looking at, a certain angular size. And then if you follow the same kind of ideas going through the glass, the image looks much bigger. So that's essentially how they work. Now, you probably, no doubt, anyone in astronomy have heard of Johannes Kepler. He did a big study on optics, and he looked at the telescope and decided that you could do much better having a concave convex eyepiece lens, same as the objective. And the main advantage is that you get a better field of view. It doesn't look like you're looking down a narrow drain pipe. But these early telescopes, the field of view was very narrow as far as, it looked to the eye anyway, so this was a bit of an improvement. And you notice that the image is flipped. So that means that it's maybe not so good for terrestrial use, but fine for astronomy. Same century, the other main type of telescope was invented, known as the Newtonian reflector. Of course, invented by Sir Isaac Newton. Newton realised that as well as using a lens to focus light, you could use a curved mirror. So, and this design is essentially identical to modern day Dobsonians or Newtonians. It's still in use today, with only the mechanics really being modified and better optical surfaces and so on, but the design is essentially the same. Whereas the refracting telescopes we were looking at before, they've undergone some fairly major design changes to overcome the flaws. So what's the principle behind it? So this is showing a collimator with a beam of light bouncing off a flat mirror. And the key thing here is that the angle of incidence is equal to the angle of reflection. And we sort of, if you're familiar with mirrors, you sort of know this instinctively, that if you want to see yourself, you have to look directly at the mirror in front of it so that the light reflects straight back at you. If you want to see something over to the side, you move to the opposite side and you get the that angle. And it doesn't take too much to figure out that if the mirror is curved, you can use this rule, just the angle of incidence is equal to the angle of refraction, to focus light in just as much the same way as a lens does. So these days you can make pretty easily, amateurs often make these reflecting Newtonian type telescopes. Not as common now because you can buy them probably more cheaply than you can make them. So, but it used to be a big thing, amateurs making their own Newtonian telescopes especially. So the main thing you need is that you have a first surface mirror. So a bathroom mirror is no good where the glass is in front of the reflective surface, because that's going to introduce optical aberrations, so that's no good. And nowadays the coatings can be either aluminium or silver. Used to be used, and it still can be used if you put a protective coat over it. The problem with silver is that it tarnishes quite rapidly, whereas aluminium will form an oxide layer that actually protects the surface, and the oxide, is, as long as it stays thin, is quite transparent. But you can also get the more modern way of doing it, is even with the aluminium, is to use a vacuum chamber to overcoat the aluminium with silicon dioxide, which has two advantages. It stops the oxidation of the aluminium, but it's also a lot harder than aluminium, so it makes it resistant to scratching from if you accidentally rub dust on it or that kind of thing. So a lot of the good quality mirrors you buy these days for astronomy will have that protective overcoat. Okay, just a little bit on, we had the example of how reflection works. Refraction is a little bit trickier. And you see in this example, the beam comes down, hits a flat piece of glass, and there's still a little bit of reflection. You probably realise, you look at a glass surface, there's a faint reflection, so that's sort of indicated by the faint beam heading off at 60 degrees. But most of the light, if it's a good quality glass, will go through. but it doesn't go through straight, it actually gets bent, and that's known as refraction. And we won't dwell too much on the next slide, but this is basically how it works. It's a bit more complicated than the angle of incidence is equal to the angle of reflection. What we have is that you've got a number of different numbers there. You've got important ones, N1 and N2, the property of the substance. So N1 we could say is air, so the beam of light is coming through air. Then it goes through glass, which has a different value of N, called N2, and then you can use this formula here to figure out the angle that the light gets deflected. The value N is what's known as the refractive index. Different glasses, types of glass, will have different properties that give them different refractive indices. And the physical reason this happens is that the light actually changes its speed when it goes into a different medium. Heard about the speed of light as a constant. Well, that's true in a vacuum or pretty much through air, because the refractive index of air is very close to being 1. But in other substances, light actually goes slower. So the propagation of light through optical glass is slower than it is through the air. So here's the first issue that comes up with refraction, is that it not only deflects the light, the amount by which it gets deflected not only depends on a single number of refractive index, it depends on the colour or the wavelength of the light. So glass, refractive index of glass varies according to the colour of the light. So that immediately causes us some problems with refractors, because when the light comes in, it's multiple colours. It will cause the light of different colours to focus at different positions. So that was the issue they had with the early refractors. One way of sort of getting around this was to not bend the light too much, use a really long focal length, but then your telescopes get incredibly unwieldy if you do that. If we just show you an example of how this works. This is a graph of different kinds of glass, optical glasses, and shows you the wavelength of the light along the bottom and the change of refractive index with wavelength. And you can see that the different glasses are quite different in the effect they have on light. But this is actually quite useful, because by combining these in the right way, you can actually cancel out the dispersion of the light into different colours. So with a bit of clever optical design. So this is what happens with a single lens. So nobody would sell a telescope with a single lens these days, because it would be pretty terrible. Either that or have an incredibly long focal length. So you can see what happens. The blue light is getting refracted more in this example, and so you can't get all three colours to focus at the same place. In the old days, they didn't have any choice, so you ended up with telescopes like this, which is a bit extreme. Interesting mount. Well, yeah, you get a lot of really high magnification with a telescope like this. The focal length must be, what, about 20 metres or something more, probably.
Oh yeah, these are crazy.
So somebody, actually a barrister, Chester Moore Hall, and also another gentleman named John Dolland, realised that you could, with a bit of trickery, combine two different glass types For example, it shows the crown in flint glasses, and it almost gets there. You can design the lens to bring two colours to focus, but the third one is going to be still slightly out of focus. Which one you choose to be in and out of focus, the designer can choose. Quite often it's the blue end of the spectrum that they design to be out of focus, and this is where, if you see a cheapish refracting telescope, you'll notice on bright objects you'll see a purple fringe. So you'll still see that today with a type of lens called an achromat. Otherwise, some of these achromats give really nice images, but you will get this annoying purple fringing or violet fringing on really bright objects. So we can go one step further, and it's quite common to have refractors that use glasses with really unusual optical properties, often fluorite or similar types of optical glasses. And you can actually then, with appropriate design, bring all of the colours to the same focal point. These lenses were really expensive if you go back before the turn of the century. Now they're not so uncommon, but they're still more expensive than an achromatic refractor. But you'll notice if you look at many of the websites that sell quality astronomical refractors, they talk about apochromatic lenses, and they are more expensive, but not to the extent they used to be. So amateurs do own these. I think one of our members, Kevin Barker, actually has a Zeiss one, which was one of the early ones of these, quite a rare collector's piece. One of the thing about some of these special glass types is that they're quite often quite soft, so it restricts the designer that they can't really use the first lens made out of that material because it's too easy to damage or scratch. So the designer will either make it the second lens or the third lens where it's not going to be subjected to any physical bumping or dust or whatever, scratching, anything like that. So probably if you want to get really good images with a refractor and you don't want to or don't mind spending a bit more money, then that would be the way to go. So but there are people who swear by refractors and they love them for everything, for photography or just visual observing, because you do get, it's well designed one, you get really nice contrast. Okay, yeah, there's still some high-end ones of these APOs available and still quite expensive. So we already put up a picture of Sir Isaac Newton's Newtonian telescope. The Society have got several of these that are mounted on a Dobsonian, basically a rotating rocker box type mount, but the telescope is a Newtonian. And this is how it works. You have the primary mirror, which is curved to focus the light. Light gets reflected back down the tube to a secondary mirror, which is flat, and they're usually elliptically shaped so that when you look at them through the focuser, projects as a circle. And then you put your eyepiece in the focuser on the side of the tube. So the big advantage of these is that you get a really good bang for buck with these, because the optical components are relatively cheap to make, so you can make a large mirror. The secondary flat mirror is quite cheap. So if you like lots of aperture, then this type of telescope is the way to go for your money. So the original idea was just to have a spherical mirror with a reflecting telescope, but there's a problem with that when you get away from the central part of the image, what's known as off-axis, you start to get an effect called coma, which is an optical aberration, so the light isn't properly focused. Can show that with a diagram shortly. But to get around this, you can use a parabolic mirror. The spherical one also has a thing called spherical aberration, where light reflected off different parts of the mirror don't come to quite the same focus. You can get around this by using a less curvature, so a longer focal length, a bit like they did with the refractors in the old days. It's possible to correct some of these aberrations with basically a sub-aperture corrector that you'd put in the eyepiece holder, but the best way is to basically not make the curvature of the main mirror too high, so that you get a reasonable focal length and you have a parabolic shape. Now, another type of telescope that's used a lot is what's known as a Cassegrain, where you, instead of having a flat mirror projecting the image out to the side, you have a curved secondary mirror which focuses the light through a hole in the primary mirror. And telescopes of this type are like the Zeiss telescope upstairs. If you've had a look at that, this is exactly this design. So you get pretty good images. The secondary mirrors are a little bit harder to make because you've got to get the curvature correct. And the other advantage over a Newtonian of these is that you can you've basically folded the telescope, so you get a longer focal length and a much shorter tube. So, for example, the Zeiss telescope has a focal length of 6.5 metres. I think that's right, 6.5 or 6.6 metres. But obviously the telescope isn't that long, and that's because it's basically folding the path of the light. And the secondary mirror is also providing, I guess you could call it magnification, or effectively increasing the focal length over the simple distance the light is travelling. It's called apparent focal length. Another reflector, the Society owns one of these. This is the one installed at the Kew Observatory. So this is a Cassegrain design, but it's got a more complicated optical design where both mirrors are hyperbolic. Because that's harder to do, these telescopes tend to be more expensive than this Cassegrain. But the advantage is that you get, they correct most of the optical aberrations, so you'll get sharper images at the film plane, especially when you move to the outer parts of the image. The difficulty of these is that they're really difficult to collimate, which I think Steve can attest to. Because of the shape of the mirrors, the alignment has, not only that, the design requires the mirrors to be at a fairly exact distance apart, whereas Cassegrain and Newtonian are a bit more forgiving. Well, the Newtonian, as long as you intercept enough of the light, the distance between the primary and secondary doesn't really matter too much. All of the, or nearly all the professional observatories use this design. The Hubble Space Telescope used this design, although I think the main mirror as launched was shaped incorrectly, and I don't know if you remember, they had to have a special mission to send an optical corrector up to fix the the problem, that it had been perfectly ground and polished to a shape, but it wasn't the correct shape. There was a bit of a stuff up with that. But by analysing the images, they were able to figure out what had gone wrong and fix it up with a correct sub-aperture corrector. Okay, we move away from, we've talked about refractors and reflectors of different types. The next one is a type of telescope that is called a catadioptric telescope. And these are like a hybrid design because they have both reflective and refractive elements. And for amateurs, probably the most common ones, especially the most common, is the Schmidt-Cassegrain. There's also the Maksutov telescope. The Maksutovs are usually smaller apertures. I don't know, a few years ago, a little tabletop telescope called a Meade ETX used to be around, was a Maksutov. The Society actually owned quite a large one, a 12-inch one, but it's big and heavy and really it needs an observatory, and so it's been sitting in storage, unfortunately. So let's have a look at the Schmidt-Cassegrain. So the way the Schmidt-Cassegrain works is that you have a corrector plate, which is an optical glass at the front, and that does a really small adjustment to the incoming light. So it's minimal chromatic aberration, but it's enough to fix the optical aberrations you'd otherwise get, like spherical aberration, and it corrects quite a lot of coma, but not all. There are some newer variants that fix most of the coma as well. So you have this glass plate, and then the secondary mirror is actually mounted in the middle of the glass plate, and it will normally, doesn't show it here, but will normally have collimation screws to adjust the tilt of it. And some versions of these actually focus by moving the main mirror, which seems kind of strange, rather than having a focuser at the back. Sorry?
Most of them do.
Yeah. But it is possible, especially if you're doing astrophotography, to lock the mirror into a position and then have a more normal focuser at the back. So again, these people like these because they're quite compact. So you can get a say a 10-inch telescope, and most of them, the designs from the main sort of commercial manufacturers are around f10. And if you find that a bit too slow, too long a focal length, you can use a device called a focal reducer. And people who use them for astrophotography will often combine a focal reducer, which we will explain in the accessories part. So pretty popular. Astron sell Celestron ones nowadays, and they're the more common one. There used to be Meade competing, but I believe Meade has gone broke, which is very unfortunate. Oh yeah, and just to show you what a Maksutov, it also has a corrector, but it's a much thicker and heavily curved corrector. And the interesting thing is that the secondary mirror it just uses the backside of the corrector. You just basically put a silver spot in the middle of it, and that acts as your secondary mirror. And these give very good optical quality. The downside of them, that because of that really massive corrector lens, is that they've got a lot of heavy glass in them, and they take I believe they take quite a long time to cool down, especially if you have a large aperture one. So if they're carrying heat from the day into the night, they take quite a long time to reach thermal equilibrium, which causes problems with observing. Okay, these diagrams are probably a bit more complicated than they need to be, but we already talked about the two schemes, the Galilean scheme with the negative eyepiece and the Keplerian telescope with the positive or convex eyepiece. So I don't know whether any of these really exist these days other than museum pieces, but pretty much all modern refractors are based on this idea, except for obviously the extra objective lenses to correct the aberrations. So let's turn to eyepieces. If you're doing visual observing, your telescope isn't a lot of use without one. You could view at prime focus, but it's not really going to work very well in an amateur telescope. I'm told that people have observed at the prime focus of the Mount Wilson 100-inch reflector, so it is possible. The first thing you need to know about eyepieces is the barrel size. Not very common these days are these 0.965 inch. Sometimes department store telescopes still have them. They were used on some high quality telescopes in the past. Like when I was a teenager, I used to drool over the Questar advertisements on the back of Scientific American. They had these really nice, I believe they were Maxitov actually, and they were a top quality tabletop telescope, and they used 0.965 inch. Seems a weird number. I don't know what the history behind that is, but they had really high quality eyepieces as well, so they were in a bit of different league to the department store scopes. Okay, the other thing is, what is these days the two common ones is a 1 1/4 inch. Generally, telescopes that you buy these days mostly come with a 2-inch focuser for visual work, and you can use either 1 1/4 or 2-inch eyepieces. You need an adapter for the 1 1/4 inch ones. It's just basically a metal adapter you just put in that's got a smaller hole in the middle to take the 1 1/4 inch eyepiece. Generally, the shorter focal length eyepieces that you use for high magnification will come in a 1 1/4 inch size, and then the wide angle, longer focal length eyepieces will have the 2-inch barrel size. And the focal length eyepieces have a focal length, and the focal length basically sets the magnification of your telescope. It's a simple formula relating the focal length of the telescope and the eyepiece to give you the magnification. So another property of eyepieces is what's known as the apparent field of view. Mentioned before that some of the old-fashioned telescopes were a bit like looking down a drain pipe. So the apparent field is how wide the view looks to your eye, and this can typically range from maybe less than 40 degrees, which is almost getting drain pipe-ish, to over 100 degrees apparent field of view. Generally, as you go up in field of view, the price of the eyepiece goes up. So okay, so a common design used for amateurs is what's known as a plosser, which has 4 glass elements in it. Its field of view is a bit over 50 degrees. And then these are a couple of more advanced designs. These are teleview eyepieces, and you can see they're getting quite complicated with the number of lens elements inside them. And if you were buying say an 8-inch Dobsonian, what do they cost now? About $800 or $900. So these eyepieces actually cost more than the telescope if you want to invest in these high-end ones, as they're called. The top one is a Nagler Type 2, 82-degree field of view, and it works down to a focal ratio of f4.5, so they work really well with fast telescopes. Longer focal length is no problem either. And then the newer design is the Ethos range, which has a 100-degree field of view. Okay, so that's a little bit about eyepieces. Another thing we will often use with telescopes is, remember we had a negative eyepiece in the case of the Galilean telescope. We still do use a negative lens, but not as an eyepiece. We use it to increase the apparent focal length of the telescope, and you can see how it works. That the negative lens known as a Barlow lens, it's normally a doublet to get rid of optical aberration as much as possible. But if you follow the lines back from the focal point, it increases the effective focal length. So in other words, it looks like the objective is further away. And so typical Barlow lens, you get a ×2 Barlow, effectively doubles the focal length of the telescope. The reason you want to do this is twofold. So if you're observing planets when you want a lot of magnification, and you'd have to use a really, really short focal length eyepiece to get high magnification. There's downsides to that. Or you can combine an eyepiece with a Barlow lens that effectively halves the focal length of the eyepiece, or doubles the magnification depending on which way you look at it. So yeah, if you're doing observing and you want to observe the planets, it's quite common to use a Barlow lens. The other thing that a Barlow lens does is, we haven't talked about it yet, but there's a thing called eye relief. And the eye relief is how close you have to get to the eyepiece to see the whole of the field of view. So if you wear eyeglasses, like if you have astigmatism and you need to wear eyeglasses to observe, then a Barlow lens can be really useful because longer focal length eyepieces tend to have more eye relief, so they're easier to use with eyeglasses. So you're not locked out of high magnification. You can get a 2 or 3 times Barlow lens and still observe comfortably with eyeglasses if you need to. Okay, another accessory that this would be really one mainly used for astrophotographers. So you want to actually reduce the apparent focal length. So it's doing the opposite of a Barlow lens. So the reason you would do this is that you want to have an image that isn't so magnified on your CCD or whatever you're using to take the image. Basically, you concentrate the light into a smaller area so you get faster exposure times and you're not really worried about superfine detail. So things like imaging galaxies and nebula. Another thing that you might use if you're doing photography is what's known as a field flattener. This is a ridiculous exaggeration of the issue, but it's showing the different light coming in from different angles where the light gets focused, and you notice that it isn't a flat plane. So the blue rays are getting focused up there, the red is where you want it to be, and so on. So the problem here, this is what is known as field curvature. Now, if you have, obviously, generally a film or a CCD is going to be flat. So what this means, if you have field curvature in your telescope, and most designs will have some field curvature, if it's a chip that sort of only covers this central area, then it's not too much of a problem. But if you want to have say I don't know, a medium format camera or even a full frame camera, you might start to realise that in the corners, the stars are a bit out of focus, and that's caused by field curvature. And you can get a device called a field flattener to correct this. The problem with field flatteners, they're not generic, they have to be designed for your optical system. So generally the manufacturer of that scope will sell a field flattener that's designed to work with that telescope. Okay, another thing that you might use is filters. And the obvious one, or the simplest one, is probably the neutral density filter, or sometimes called a moon filter. Quite often when you buy telescopes, they are for visual observing, they may include a moon filter. So what these do is that they are good optical quality, so they're not distorting the image in any way, but they just basically attenuate some of the brightness. So I don't know if you look at the moon through a telescope, it is quite dazzling. So to be able to observe the moon comfortably, people will often use a neutral density or a moon filter, as they're called, for observing the moon. And of course, the extreme example of this is mentioned at the bottom, as if you're observing the sun. You obviously never look at the sun through an unfiltered telescope. And this type of neutral density filter is no use for looking at the sun. It would be really dangerous. So you need a special type of filter designed for viewing the sun. So other ones can be used. There's a thing called a UHC filter, which was quite useful in city when there were a lot of sodium vapor lights around. These give out a really yellow frequency, so you could filter that light out and observe even when the sky wasn't otherwise so good, because most of the background light from your city was this yellow colour from the sodium lamps, but unfortunately that isn't true anymore because most of them have been replaced by LEDs, which are broad spectrum ones. But people for photography or even visually observing nebulae especially, there's various types of filters that you can use that give better contrast. For example, for a planetary nebula, an O3 filter, oxygen doubly ionised. Okay, and again, do not use any of these three types for the sun. Okay, we have to have some formulas, I guess. Hopefully they're not too complicated, but we start off with some definitions. And the first thing is, capital D, is the aperture size of the primary lens. Now that formula there, the sine of some angle theta is equal to 1.22 times lambda, which is the wavelength of light, divided by D. What that is the giving you the angular resolution of your telescope. So the bigger D is, the smaller this angle, so the more you can resolve. It'll resolve finer and finer detail. Unfortunately, you reach a limit down here at sea level where the atmospheric turbulence will be greater than the resolving power of your telescope. So you end up with a limit, and this is why they often put telescopes up on mountains to reduce this effect, or even better, put them into space where you don't have the problem of the atmosphere. In space, of course, the bigger the aperture, the better, or professional astronomers on high mountains, more aperture means not only more light, but more resolution. So the other thing is the focal ratio of the telescope, and that is the basically the ratio of the focal length divided by the diameter or the aperture. And then we've got some other things: focal length of the telescope, focal length of the eyepiece. We have a apparent field of view of the eyepiece, true field of view. So the true field of view is how much of the sky you can actually see, and that's a property of the combination of the telescope and eyepiece. We have a thing called the exit pupil size and the eye relief. These are all things that might be of interest to amateur astronomers. And finally, the magnification. And usually we don't care too much about magnification, but we may need that for observing planets. Because the problem is, if you can easily increase the magnification by stacking barlows or using shorter focal length eyepieces, but the problem is that reduces the brightness of the image. So it's okay for planets to do it because planets are really bright. But if you do this with a galaxy, you're just going to make the galaxy more and more dim. So beware of any telescope that's sold quoting 600 times magnification or anything like that. Sure, you might theoretically be able to do it by stacking barlow lenses, but the images will be terrible. But we do use it when you have a bright object that's small, like a planet. So here's our formulas. Hope they're not too tricky. Focal length of the telescope is the diameter divided by the focal length, or the aperture divided by the focal length. An example, the type of telescopes we hire, most of them are 8-inch or 200mm f6. So in that case, you can calculate the focal length of one of those telescopes is just 1200mm. And if you want to know what the magnification of those is with a particular eyepiece, you just divide the focal length of the telescope by the focal length of the eyepiece. So same telescope, 200mm f6 with, in this case, a 25mm eyepiece. So that's giving you 1200 divided by 25, or 48 times magnification. So obviously if we use a shorter focal length eyepiece, because we're dividing by that, the magnification increases. I know Gareth, when he was at public events, he'd show two eyepieces and he'd have a big one and a little one, and he'd ask the public which one will give us the most magnification, and people point, oh, the big one, but it's actually the opposite. Okay, the other thing is you might occasionally want to know, like if you're star hopping, this is quite useful to know, is how much of the sky are you actually looking at to be able to compare with your star chart or your stellarium or your phone star chart. So you've got the apparent field of view. Now you have to get that from the eyepiece manufacturer. They will publish what the apparent field of view of the eyepiece is. You divide that by your magnification and that gives you the true field of view. So an example would be, so if we use a Plossl eyepiece, apparent field of view about 50 degrees. They do vary a little bit again. You have to read the manufacturers, or if you don't trust them, you can actually measure it and I'll tell you how you do that. So if you've got one of these 25mm Plossl eyepiece, 50 degrees apparent field, then again with the same Dobsonian telescope, 200mm f6, the true field of view is going to be just slightly over 1 degree, so roughly 1 degree with a 25mm Plossl eyepiece. So just a lot of words here. If you're interested, you can actually measure the true field of view. If you have a telescope that doesn't track, point it at a star near the celestial equator and just time how long it takes the star to drift across the field of view. And we know that we can the true field of view, we can use this formula, time to drift in minutes, times 15 divided by 60. So if you know the true field of view, you can actually work backwards to calculate the apparent field of view. So if you had an eyepiece, you didn't know what the apparent field of view is, by timing how long it takes to start a drift across the view, you can roughly calculate the apparent field of view. Okay, getting near the end. This is a thing called exit pupil. Now, the exit pupil is equal to the focal length of the eyepiece divided by the focal ratio. So an example, you can actually, if you hold a pair of binoculars up and at a bright source, you can actually see sort of like a circular bright patch. That's actually viewing the exit pupil of the binoculars. And the reason it can be important is to do with your eyes. So if we have an exit pupil, say it shows a 30mm eyepiece divided by an f6 telescope, means the exit pupil is 5mm. So what does that mean? Well, how wide does your pupil open? If the exit pupil is greater than your actual pupil size, then you're not getting to all the light, so you'll get a dimmer view because some of the light is actually not getting into your eye because your pupil isn't opening wide enough. This is why cats can see better in the dark than us, because their pupils can open really wide. So it's effectively the aperture of the eye. So typical human, if you're fully dark eye adapted, the pupil of your eye opens to about 6mm, but it varies, and as you get older, it actually becomes less. So your eyes don't adapt as well when you get older because I don't know whether it's the muscles get weaker or something that open the iris of the eye. So, for example, if you're using a really long focal length eyepiece, 40mm eyepiece, with this telescope, the exit pupil is going to be probably more than you can accommodate with your eye, which means that you're wasting some of the light. Even though you're getting a wider field of view, it'll be dimmer than you would expect. So you might have to get your cat to observe in that case. So I think that's about all for tonight. We've got any questions or comments about telescopes or eyepieces or tips or anything like that? Oh, yeah.
Yeah, what is the advantage of a parabolic mirror over a parabolic?
Oh, I didn't really show a diagram of it, but if you're looking at a Newtonian design and you ray trace it out, what you find is that a spherical mirror, the light reflected from the outer part of the mirror doesn't come to the exact same focal point. It's an optical error called spherical aberration. And if you have a parabolic mirror, then the rays that hit the outer part of the mirror, or part way between the middle and the outside, they all come to the exact same point in the centre of the field. So that's why a parabolic mirror is used. It still isn't free of optical aberrations. I think I mentioned that when you go away from the centre of the image, you start to get another effect called coma. I think I did mention it, but I didn't really explain it. And you can't correct that just with a parabolic mirror. It's possible to correct it with a sub-aperture lens, or in the case of some of those other designs like the Ritchie-Kratian, mostly eliminates coma, and there are variations of the Schmidt-Cassegrain that eliminate coma. I think Grant's, you've got a coma-corrected Schmidt-Cassegrain up in the other dome, I believe.
Yeah, well, probably a lot more complicated.
Yeah. Yeah, well, that's a combination of corrector lens and different shaped. It's not simple. They don't use a simple shape for the mirrors to correct the coma. But yeah, that's why one of the reasons professional scopes, they like the Ritchie Creation design with the hyperbolic mirrors, because that actually eliminates coma over the field they're interested in. It isn't really a problem generally for visual observing. You might notice it with really fast Newtonian, but definitely at f6, you don't really notice it, definitely not visually. If you're really fussy and you're doing photography, you may notice it with a camera, but it isn't really an issue for visual observing. Okay, well, Andrew isn't here to tell us what wonderful deals he's got, but anyway. Okay, thanks for coming along, everyone.